Hello everyone. In this lecture, we are going to solve examples on the shortcut method for finding particular integral when the right hand side function is the exponential function. So let us go to the example. Example is solve the differential equation d square plus 3d plus 2 of y is equal to e raised to 2x. So this is second order non-homogeneous linear differential equation. Solution. Auxiliary equation is d square plus 3d plus 2 equal to 0, whose roots are d equal to -1 and -2. There are two roots as order is 2, which are real and distinct. So therefore complementary function is yc equal to c1 e raised to minus x plus c2 e raised to minus 2x. Now we will find particular integral. To find particular integral, its formula is what? General formula yp is equal to 1 upon phi of d of f of x. Here phi of d is d square plus 3d plus 2 and f of x is e raised to 2x. As per our first case that we studied in the last lecture, whenever exponential function is there, we have to replace this d by the coefficient of x in the exponential function. In this case it is 2. So replace d by 2. That will give us, so 1 upon d square. 2 square is 4 plus 3 into 2 is 6 plus 2. Simplify it. That will give us yp equal to 1 upon 12 e raised to 2x. So this is the required particular integral as we got the non-zero denominator. So we obtained both yc and yp. Hence, general solution of the given differential equation is given by y is equal to yc plus yp. Replace this yc and yp by their corresponding expressions. We will get general solution as y is equal to c1 e raised to minus x plus c2 e raised to minus 2x plus 1 upon 12 e raised to 2x, which is the required general solution. Now we will go to the next example. Second, solve the differential equation d square minus 6d plus 9 of y is equal to e raised to 3x plus 9. Solution. Auxiliary equation is d square minus 6d plus 9 equal to 0. So this is the expansion of d minus 3 square, and hence roots are d equal to 3 comma 3, which are real and repeated. Hence complementary function is yc is equal to, for the repeated root, recall the procedure how to get the complementary function. So which is c1x plus c2, as there are two roots, so two arbitrary constants, c1x plus c2 into e raised to 3x. This 3 is from the root itself. Now we obtain particular integral. General formula is 1 upon phi of d of f of x. Phi of d is what? D 1 upon d square minus 6d plus 9. So phi of d is d square minus 6d plus 9 and f of x is e raised to 3x plus 9. The right hand side function in the given non-homogeneous differential equation. As there are two terms in the given functions, so we will operate this operator separately on each of these two terms or the functions. That will give us expression like this. So this e raised to 3x as it is, but we have seen in the last lecture, if the constant term is there, then how to evaluate particular integral in that case. So 9 can be written as 9 into e raised to 0x. And now use the first case. So what it will give us? So replace d by 3 here, and in the second term replace d by 0. So that will give us yp is equal to 1 upon 0 e raised to 3x plus 1 upon 9 into 9. So see, when we replace in the first term d by 3, the coefficient of x in the exponential function, our denominator became 0. So here first term is the case of failure. So in that case, how to evaluate particular integral further? Recall the procedure again. So what is the formula? So if there is a case of failure, then the particular integral will be evaluated as x upon phi dash of a e raised to ax. How to get this phi dash of a? For that, first we need to differentiate the given polynomial phi of d. So using which we will be getting yp is equal to x divided by, see, this 2d minus 6 is the derivative of 2d d square minus 6d plus 9, and therefore x divided by 2d minus 6 e raised to 3x plus 9 upon 9 is 1. So see, using this formula we rewritten the first term like this. So that will give us the particular integral further. So again, as it is an exponential function, again replace this d by 3 and see what we will be getting. So that will give us again 0 in the denominator. So x upon 0 e raised to 3x, which is the case of failure again. So in this case, again we will use our next formula, which is 1 upon phi of d of e raised to ax. So if second time denominator is becoming 0, then in that case, the particular integral will be evaluated using the formula x square upon phi double dash of a of e raised to x, means we have to differentiate this phi of d twice with respect to d and evaluate its value at point a. So the second order derivative of phi of d, which is d square minus 6d plus 9, will be what? 2. So that derivative will be x square upon 2 e raised to 3x plus 1. As we left with no term in d in the denominator, so this is our required particular integral for the function e raised to 3x, and this whole term is the particular integral of the given differential equation. Hence, the general solution will be given by y is equal to yc plus yp. Replace these functions yc and yp by their corresponding expressions. That will give us the required general solution as y equal to c1x plus c2 into e raised to 3x plus x square by 2 into e raised to 3x plus 1. I hope you got this example. Now let's move on to next example. Solve the differential equation d square minus 6d plus 5 of y is equal to e raised to x plus 2x. Let us see how to solve this. Solution. Auxiliary equation is d square minus 6d plus 5 is equal to 1. Roots are 1, 5, which are real and distinct roots. Hence, complementary function is yc equal to c1 e raised to x plus c2 e raised to 5x, which is the required complementary function. Now we will find particular integral. Yp is equal to 1 upon phi of d of f of x. This is general formula and we have to always mention it in our answer. Phi of d is d square minus 6d plus 5 and f of x is e raised to x plus 2 raised to x. Again there are two functions in f of x. So we'll operate this operator separately on each of these two functions. This will give us expression like this. Now for the first term, replace d by the coefficient of x, which is 1, and this is of the type a raised to x, where a is 2. So in this case, d will be replaced by log 2. That will give us yp equal to 1 upon 0. So see, for the first term here, denominator became 0. So 1 upon 0 e raised to x, which is case of failure, plus. For the second term, we replace d by log 2. That will give us 1 upon log 2 bracket square minus 6 log 2 plus 5 into 2 raised to x. Now we will evaluate this term further as it is a case of failure. So again we will use this formula. 1 upon phi of d of e raised to x is equal to x divided by phi dash of a e raised to x. For which first we need to evaluate phi dash of d, which is, so yp is equal to x divided by 2d minus 6, which is the derivative, first order derivative of d square minus 6d plus 5. Hence we got here x divided by 2d minus 6 of e raised to x plus 1 divided by log 2 square minus 6 log 2 plus 5 2 raised to x. Again, as it is exponential function, replace here d by coefficient of x, which is 1 here in this case. So that will give us, so replace d by 1, that will give us 2 minus 6 is minus 4. So yp equal to minus x upon 4 e raised to x plus 1 upon log 2 square minus 6 log 2 plus 5 2 raised to x. See, as we got non-zero denominator in the first term, so this is our particular integral, and hence the general solution is y is equal to yc plus yp. Replace these yc and yp by their expressions. So that will give us general solution as y is equal to c1 e raised to x plus c2 e raised to 5x minus x by 4 e raised to x plus 1 upon log 2 bracket square minus 6 log 2 plus 5 into 2 raised to x. So which is the required general solution. I hope you have understood this. Thanks for watching this video.